Well, thank you for the presentation. Um, Today I'm going to talk about um, this work of a rapid update mesoscale data simulation for a mid-latitude high-impact weather event, which is part of my master's degree, supervised by uh, Juan Ruiz in Yanina, Garcia, Skabar, and well, with collaboration with another researchers here. So, as everyone knows, deep moist convection can cause high impact weather events such as severe weather or crop loss. So it becomes essential uh, the enhancement of our forecasting capabilities through numerical weather prediction models, but also its combination with the assimilation of data at mesoscale. So here we test the sensitivity of forecast skill to horizontal resolution and radar data assimilation frequency. And particularly, we evaluate the impact of these factors on uh, the environmental conditions, the deep moist convection, and practical predictability of a case study that is the same that Federico presented a few minutes ago. So I won't take too much time here, but I just want to say that this event was characterized by, let's say, two convection regimes. The prefrontal convection, which was this two isolated left-moving supercells. Here you have the trajectory of the core of the most intense one. And after this event, we had a frontal force convection associated with an extratropical cyclone. And here you have the mosaic for these two, the prefrontal and the frontal convection, and the environmental condition, the sea level pressure and the wind at 10 meters and the most unstable cape. And well, here you have the Hill reports of the prefrontal convection. And so our observation network that we use for data simulation integrate the radar reflectivity and Doppler velocity derived from the Argentinian radar networks in black stars and these circles, the surface stations in red and purple, and radio zones in blue. And well, we have another, as we assimilate another type of observations that are not present here, but these are. And our experimental setup, as you can see here, we have 5 numerical experiments. All are ensemble based with 60 members, and all use a multiphysics approach. So different groups of members represent the subgrid scale processes using different physical parameterizations. We have 3 of these 5 experiments that are that use data simulation with the WRF LETKF system. And we also have these 2 no data simulation, low and high resolution WRF runs initialized from the GFS. So these 2 don't have data simulation at all. And it's important to mention that all are convection permitting. So the cumulus scheme is not used in this case. And to point out that these 3 data simulation experiments have the assimilation frequency of 1 hour and 5 minutes for this low and high resolution. When I say low resolution, it's 4 kilometers, and high 2. So moving to the results, we have here the impact of data simulation on environmental conditions. For example, in this figure, we have the analysis ensemble mean of most unstable cape and maximum radar reflectivity. Here the observations and the 3 assimilation experiments. And as you can see, the assimilation experiments capture the observed convection location, but it's better performed by the highest frequency ones. But not everything is perfect in this case. These 2, but mostly the high resolution one, exhibit spurious convection, and this seems to be associated with the high frequency data assimilation of um, um, surface stations. Here, this scatter here is the purple and red. It's the position, the location of surface stations, and they are in the same places of the local maxima of most unstable cape. Here, to have a more general view of the scale of the whole analysis period, we perform this time series of the scale of analysis ensemble mean with two thresholds of 30 dBc and 40, and a fixed neighborhood of 30 kilometers. You can find here the probabilistic fraction skill score in this paper of Necker and others in 2024. And we can see higher values of skill, except for these three specific times with low reader coverage and with random effect. And looking at the prefrontal convection representation in the analysis ensemble of these three assimilation experiments, we can see here in the first column the reader observations for 3 different times, and these three assimilation experiments. We can see, for example, that the hourly data assimilation experiments misses completely one of the supercells in the analysis. It was unable to represent it, but the data with the same resolution, but 5 minutes, 12 times higher the data simulation frequency, we can represent the pattern, a similar pattern for the observations, but the most consistent experiments in terms of supercell intensity and dynamics is the high resolution one. For example, with the intensity of its updraft and the position of the maximum reflectivity. Here, in order to show you the relevant impacts of data simulation forecast, we perform this Hofmöller of this is the data simulation high resolution experiment analysis with ensemble probability. And in the background, we have the most unstable cape of Möller, and this is the binary mask of radar mosaic, also the Hofmöller. And in these 3 times, we show you the 3 different initializations, 3 different forecasts using the same analysis, and to compare how well was this forecast, we show you the no data simulation high resolution also. And as you can see, initializations generated by shorter assimilation periods, for example, this initialization, propagates some prefrontal convection, and the no data simulation experiment was completely unable because of the spin up that needs to generate the convection from the GFS initial conditions. But as the assimilation period, we know that as the assimilation period gets larger from 1821 and 06 UTC, that it's the last available, the latest available initial condition, the environmental instability in the data simulation high resolution experiment is reduced. So is the likelihood of deep convection. As you can see, the difference of the most unstable cape in these two and the reduction of the intensity of the probability of reflectivity is visible. So it appears that the data simulation high resolution with the longest assimilation periods does not perform better than the no data simulation high resolution in the latest initializations. And this could be due to the excessive spurious convection that you can see in this region in the north, for example, that it's not consistently seen in the radar mosaic Hofmöller. And to have a more general idea of the ensemble forecast skill and spread, we perform this probabilistic fraction skill score for the initializations. This is the mean temporal series of all the initializations. And for example, we can see that the data assimilation experiments are more skillful than no data assimilation ones, up to 6 or 12 hours. But although all experiments show increased skill from 10 hours of lead time, I mean these latest lead times, the no data because of due to predictability gains, no data assimilation experiments perform better at longer lead times, particularly for the later initializations. For example, this one of the 3 UTC. But during the first initializations, this blue line, it's the high resolution experiment with data assimilation, was the most skillful experiment. And we also performed this dispersion fraction skill score mean that you can find here in the paper of Day and others in 2014. That is a bit tricky because when we have higher values of this score, it means less ensemble spread. So we can see that this for example, these two time series of each experiment very similarly, indicating higher ensemble performance coupled with moderate trajectory divergence. So I mean, when we have higher predictability values, we have a higher signal in the ensemble and vice versa. I don't know how much time I have left.
You still have time. I would say maybe about 7 minutes.
Okay. So this is I will do quickly. This is a probabilistic forecast of maximum reflectivity. This is the initialized at 18 and 21 UTC with lead time to 2 hours. And it's the probability of maximum reflectivity more than 40 dBc. So this slide is just to show you that even though because these are not the highest probability values that we can see, but even though none of the experiments yield high probability values, the high resolution data simulation experiments is the most consistent spatial distribution of reflectivity, mostly in this time, for example. As a conclusion, we can say that the prefrontal organized convection representation in high frequency, high resolution assimilation experiments was notably superior to the ones who assimilate hourly. And the World Fidelity Gave system provided that advantage during the first forecast hours through frequent data assimilation, while no experiments without assimilation failed because the initial spin-up required to generate convection from the GFS initial conditions. And finally, the spurious convection degraded the initial conditions for forecast toward the end of the assimilation periods, reducing the predictive skill. And I think I don't have time, so thank you for your attention.
Thank you, Emanuel, again. A great talk. I really enjoyed the abundant use of probabilistic metrics to evaluate the convective impacts. I think that's very important. Let me just double check on the Yopod here. I see a question by Robin, who is asking, I understand that because of predictability limits, assimilating radar might only be helpful to us for shorter lead times. But for long lead times, why does the data simulation make the results worse than the no-DA experiments? I would have expected to see both to perform about the same beyond that predictability limit.
If I understood,
yeah, I believe he was referring to one of those experiments when you mentioned for some of these initialization times, the no-DA experiment was able to improve beyond at later lead times.
Yes. Yes, why, if I understand it, it's asking why seems to be better than the data simulation experiments in this lead time. Okay. Well, our hypothesis is that this spurious convection that we can see here, for example, or well, in one particular time, for example, here, in the assimilation period was had um, generated a reduction of this environmental instability that affected the initialization, but mostly the latest initialization. So it's like we start this, for example, in this case, note that the ensemble spread of the high resolution one is higher. It's lower than the low resolution one with the same assimilation frequency, and could be due that the spurious instability reduction on the high resolution data assimilation experiment. And this spurious convection didn't affect the no data assimilation experiment because they don't have this relative maxima in these areas of large density of surface stations. I don't know if I answered the question, but
I think that's a good hypothesis, right? You're connecting it to the ability of the ensemble spread to then have later impacts on the overall instability, right? The environmental impacts here. I think I can see that point. I was also actually curious about the spurious convection that you talked about in your high resolution experiments. Maybe I missed the point, but do you know why you had the spurious convection? Was it to do with the the mismatch between model and observations, or is it something else?
well, I think obviously I agree, but with this probably a mismatch, but because maybe a try bias of the model, but also we think that trying the same experiments with us not such a high assimilation frequency, for example, assimilating each 10 minutes or with a different localization radii, for example, we used at 10 kilometers. Maybe if you expand, we can find another results. But I think, for example, the localization radii may cause, may contribute with this result.
So leading to some unphysical analysis values that then lead to spurious convection. Yeah, that would make sense. Not always good to have a high resolution simulation unless proper techniques are being implemented, right? Thank you, Emanuel, one more time for the talk. I think it was very useful. So